Hey everyone, welcome to the video lecture for Unit 2, Module 5.1, and this one we're going to be talking about classes of blood vessels. As always, here are your learning objectives. Make sure you reference these when you're looking at your lecture quiz as well as your unit exam. All right, let's jump into this one. So the cardiovascular system has 5 general classes of blood vessels. Arteries carry blood away from the heart, and as they enter peripheral tissues, arteries branch repeatedly. The branches decrease in diameter. The smallest arterial branches are called arterioles. From the arterioles, blood moves into the capillaries where the diffusion takes place between blood and interstitial fluid. From the capillary, blood enters small venules, which unite to form larger veins that return blood to the heart. Blood leaves the heart through the pulmonary trunk, which originates in the right ventricle, and the aorta, which originates at the left ventricle. Each of these arterial trunks has an interior diameter of about 2.5 centimeters, or about 1 inch or so. The pulmonary arteries that branch from the pulmonary trunk carry blood to the lungs. The systemic arteries that branch from the aorta distribute blood to all other organs. Within these organs, the vessels branch into several hundred million tiny arterioles that provide blood to more than 10 billion capillaries within their own branching networks. These capillaries are barely the diameter of a single red blood cell. If all the capillaries in your blood were placed end to end, their combined length would be more than about 25,000 miles, enough to circle the planet. The vital functions of the cardiovascular system depend entirely on events at the capillary level. All chemical and gaseous exchange between the blood and interstitial fluid takes place across capillary walls. Cells rely on capillary diffusion to obtain nutrients and oxygen and to remove metabolic waste, such as carbon dioxide and urea. Diffusion takes place very rapidly because the distances involved are very short. Few cells lie farther than about 125 microns or so from a capillary. As we'll see, homeostatic mechanisms operating at the local, regional, and systemic level adjust blood flow through the capillaries to meet the demands of peripheral tissues. Blood vessels must be resilient enough to withstand changes in pressure and flexible enough to move with underlying tissues and organs. The pressures inside the vessels vary with distance from the heart, and the structures of different vessels reflect this fact. The arteries, veins, and capillaries also differ in the function, and these functional differences are associated with distinctive anatomical features. The walls of arteries and veins have 3 distinct layers: the tunica intima, the tunica media, and the tunica externa. We go through those. So 1, the tunica intima, or the tunica interna, is the inner layer of blood vessels. It includes the endothelial lining and the surrounding layer of connective tissues with a variable number of elastic fibers. In arteries, the outer margin of the tunica intima contains a thick layer of elastic fibers called the internal elastic membrane. The tunica media is the middle layer of blood vessels. It contains concentric sheets of smooth muscle tissue and a framework of loose connective tissue. The collagen fibers bind the tunica media to the tunica intima and the tunica externa. The tunica media is commonly the thickest layer of a small artery. It is separated from the surrounding tunica externa by a thin band of elastic fibers called the external elastic membrane. The smooth muscle cells of the tunica media encircle the endothelium that lines the lumen of the blood vessels. When these smooth muscles contract, the vessel decreases in diameter, and when they relax, the diameter increases. Large arteries also contain layers of longitudinally arranged smooth muscle cells. The tunica externa, or the tunica adventitia, is the outer layer of blood vessels. It is a connective tissue sheath. In arteries, it contains collagen fibers with scattered bands of elastic fibers. In veins, it is generally thicker than the tunica media and contains networks of elastic fibers and bundles of smooth muscle cells. The connective tissue fibers of the tunica externa typically blend into those of adjacent tissues, stabilizing and anchoring the blood vessels. Their layered walls give arteries and veins considerable strength. The muscular and elastic components also permit controlled changes in diameter as blood pressure or blood volume changes. However, the walls of arteries and veins are too thick to allow diffusion between the bloodstream and surrounding tissues, or even between the blood and the tissues of the vessel itself. For this reason, the walls of large vessels contain small arteries and veins that supply the smooth muscle cells and the fibroblasts of the tunica media and the tunica externa. These blood vessels are called the vasa vasorum. Arteries and veins supplying the same region lie side by side. In sectional view, you can distinguish arteries and veins by the following features. Vessel walls in general. The walls of the arteries are thicker than those of the veins. The tunica media of an artery contains more smooth muscle and elastic fiber than does that of a vein. These components help resist the arterial pressure that's generated by the heart as it pumps blood into the pulmonary trunk, and the aorta. So when not opposed by blood vessels, the elastic fibers in the arterial walls recoil, constricting the lumen. Thus, seen on dissection or in sectional view, the lumen of an artery often looks smaller than that of the corresponding vein. Because the walls of the arteries are relatively thick and strong, they keep their circular shape when sectioned. In contrast, cut veins tend to collapse in section. These veins often look like flattened or grossly distorted vessel. We can also take a look at the vessel lining. The endothelial lining of an artery cannot contract. So when an artery constricts, its endothelium becomes folded, and in the sectional arteries have pleated appearance. The lining of a vein lacks these folds. In gross dissection, arteries and veins can generally be distinguished because the thicker walls of arteries can be felt if the vessels are compromised. Arteries usually keep their cylindrical shape, but veins often collapse. Arteries are more resilient. When stretched, they keep their shape and lengthen. When released, they snap back. A small vein cannot tolerate as much distortion without collapsing or tearing. Veins typically contain valves, internal structures that prevent the backflow of blood towards the capillaries. In an intact vein, the location of each valve is marked by a slight distension in the vessel wall. In addition, their relatively thick muscular walls make arteries elastic and contractile. Elasticity permits the vessel diameter to change passively in response to changes in blood pressure. For example, it allows arteries to absorb the surging pressure waves that accompany the contractions of the ventricles. The contractility of the arterial walls enables them to actively change diameter. This change takes place primarily under the control of the sympathetic division of the autonomic nervous system. When stimulated, arterial smooth muscles contract, constricting the artery, a process called vasoconstriction. When these smooth muscles relax, the diameter of the lumen increases, a process called vasodilation. Vasoconstriction and vasodilation affect 1. The afterload of the heart, 2. Peripheral blood pressure, and 3. Capillary blood flow. We'll explore those in a later module. Contractility is also important during the vascular phase of hemostasis, when the contraction of a damaged vessel wall helps reduce bleeding. In traveling from the heart to peripheral capillaries, blood passes through elastic arteries, muscular arteries, and arterioles. Elastic arteries are also known as conducting arteries because they carry large volumes of blood away from the heart. They are large vessels with diameters up to about 1 inch or so. The pulmonary trunk and aorta, as well as their major branches, the pulmonary, common carotid, subclavian, and the common iliac arteries, are elastic arteries. The walls of elastic arteries are extremely resilient because the tunica media contains a high density of elastic fibers and relatively few smooth muscle cells. As a result, elastic arteries can tolerate the pressure changes of the cardiac cycle. We've already seen that the elastic rebound of the aorta helps to maintain blood flow in the coronary arteries. Elastic rebound also occurs in some degree in all elastic arteries. During ventricular systole, pressures rise rapidly and the elastic arteries expand as the stroke volume is ejected. During ventricular diastole, blood pressure within the arterial system falls and the elastic fibers recoil to their original dimensions. Their expansion cushions the sudden rise in pressure during the ventricular systole, and their recoil slows the drop in pressure during the ventricular diastole. In this way, elastic arteries help to make the blood flow continuous. This function is important because blood pressure is the driving force behind blood flow. The greater the fluctuations in pressure, the greater the change in blood flow. The elasticity of the arterial system dampens the pressure peaks and valleys that accompany the heartbeat. By the time blood reaches the arterioles, the pressure fluctuations have disappeared and blood flow is continuous. Muscular arteries, or medium-sized arteries, also known as distribution arteries, because they distribute blood to the body's skeletal muscles and the internal organs. Most of the vessels of the arterial system are muscular arteries. They are characterized by a thick tunica media. It contains more smooth muscle cells than does the tunica media of elastic arteries. A typical muscular artery has a lumen diameter of approximately about 0.4 centimeters, but some have diameters as small as 0.05 centimeters. The external carotid arteries of the neck, the brachial arteries of the arm, and the mesenteric arteries of the abdomen, and the femoral arteries of the thighs are examples of muscular arteries. Superficial muscular arteries are important as pressure points, places on the body where muscular arteries can be pressed against deeper bones to reduce blood flow and control severe bleeding. Major arterial pressure points are the common carotid, the radial, brachial, femoral, popliteal, posterior, tibial, and the dorsal pedal. Arterioles, with an internal diameter of 30 microns or less, are considerably smaller than muscular arteries. Arterioles have a poorly defined tunica externa. In the larger arterioles, the tunica media consists of one or two layers of smooth muscle cells. In the smallest arterioles, the tunica media contains scattered smooth muscle cells that do not form a complete layer. The diameters of smaller muscular arteries and arterioles change in response to local conditions, or sympathetic or endocrine stimulation. For example, arterioles in most tissues vasodilate when oxygen levels are low. Changes in their diameter affect the amount of force required to push blood around the cardiovascular system. More pressure is required to push blood through a constricted vessel than a dilated one. The force opposing the blood flow is called resistance, or R. So arterioles are also called resistance vessels. Vessel characteristics change gradually with the distance from the heart. Each type of vessel described here actually represents the midpoint in a portion of a continuum. Thus, the largest muscular arteries contain a considerable amount of elastic tissue, and the smaller resemble heavily muscled arterioles. Arteries carry blood under great pressure, and their walls are adapted to handle that pressure. Occasionally, local arterial pressure exceeds the capacity of the elastic components of the tunicus. The result is an aneurysm, or a bulge in the weakened wall of the artery. The bulge is similar to the bubble in the wall of a tire, and like a bald tire, the artery can suffer a catastrophic blowout. The most dangerous aneurysms occur in the arteries of the brain, where they cause strokes, or in the aorta, where a rupture will cause a fatal bleeding in a matter of minutes. And we'll talk about the circle of Willis when we are in lab, and one of the more dangerous aneurysms are where about 85 to 90% of brain aneurysms occur there in the circle of Willis. When we think of the cardiovascular system, we think of first the heart or the great blood vessels connected to it. But the microscopic capillaries that permeate most tissues do the real work of the cardiovascular system. These delicate vessels weave throughout active tissues, forming an intricate network that surround muscle fibers. Capillaries radiate through the connective tissues and branch beneath the basement membrane of the epithelia. Capillaries are the only blood vessels whose walls permit exchange between the blood vessels and the surrounding interstitial fluids. Exchange can take place quickly because capillary walls are thin and diffusion distances are short. In addition, blood flows through the capillary relatively slowly, allowing sufficient time for the diffusion or the active transport of materials across the capillary walls. In this way, the histological structure of capillaries permits a two-way exchange of substances between blood and the interstitial fluid. A typical capillary consists of an endothelial tube inside of a thin basement membrane. Neither a tunica media nor a tunica externa is present. The average diameter of a capillary is a mere 8 microns, very close to that of a single red blood cell. The two major types of capillaries are continuous capillaries and fenestrated capillaries. Continuous capillaries supply most regions of the body. In a continuous capillary, the endothelium is a complete lining. A cross-section through a large continuous capillary cuts across several endothelial cells. In a small continuous capillary, a single endothelial cell may completely encircle the lumen. Continuous capillaries are located in all tissues except epithelia and cartilage. Continuous capillaries permit water and small solutes and lipid-soluble materials to diffuse into the interstitial fluid. At the same time, they prevent the loss of blood cells and plasma proteins. In addition, some exchange may occur between the blood and the interstitial fluid by bulk transport, which is the movement of materials by endocytosis, or by endosomes, or exocytosis at the inner endothelial surface. And specialized continuous capillaries in most of the central nervous system and the thymus, the epithelial or endothelial cells are bound together by tight junctions. These capillaries have very restricted permeability. Fenestrated capillaries contain windows or pores that penetrate into the endothelial lining. The pores allow rapid exchange of water and the solutes between the blood and the interstitial fluid. Examples of fenestrated capillaries include the carotid plexus of the brain and the blood vessels in a variety of endocrine organs, such as the hypothalamus and the pituitary, the pineal, and the thyroid glands. Fenestrated capillaries are also found along absorptive areas, intestinal tract, and at filtration sites in the kidneys. Both the number of pores and their permeability characteristics vary from one region of the capillary to another. Sinusoids are also called sinusoidal capillaries, resemble fenestrated capillaries that are flattened and irregular shaped. In addition to being fenestrated, sinusoids commonly have gaps between adjacent endothelial cells, and the basement membrane is either thinner or absent. As a result, sinusoids permit the free exchange of water and solutes as plasma proteins between blood and interstitial fluid. Blood moves through sinusoids very slowly, maximizing the time available for exchange across the sinusoidal wall. Sinusoids occur in the liver, the bone marrow, spleen, and many endocrine organs, including the pituitary and adrenal glands. At liver sinusoids, the plasma proteins secreted by liver cells enter the bloodstream. Along sinusoids of the liver, spleen, and bone marrow, the phagocytotic cells monitor the passing blood, engulfing damaged red blood cells, pathogens, and cellular debris. Capillaries function not as individual units, but rather as a part of an interconnected network called a capillary bed or capillary plexus. A single arteriole gradually gives rise to dozens of capillaries. They empty into the several venules, the smallest vessels of the venous system. A precapillary sphincter guards the entrance to each capillary. Contraction of the smooth muscle cells of the sphincter narrows the capillary entrance, reducing or stopping the flow of blood. When one precapillary sphincter constricts, blood is diverted into the other branches of the network. When a precapillary sphincter relaxes, the entrance dilates and blood flows into the capillary. A capillary bed contains several direct connections between arterioles and venules. The wall in the first part of such pathway contains smooth muscles that can change its diameter. This segment is called a metaarteriole, or a precapillary arteriole. The rest of the passageway resembles a typical capillary in structure and is called a thoroughfare channel. More than one artery may supply blood to a capillary bed. The multiple arteries are called collaterals. They fuse before giving the rise to the arterioles. The fusion of two collateral arteries that supply a capillary bed is an example of an arterial anastomosis. The interconnections between the anterior and the posterior interventricular arteries and the heart are arterial anastosomes. An arterial anastosome acts like an insurance policy. If one artery is compromised or blocked, capillary circulation will continue. Arteriovenous anastosomes are direct connections between arterioles and venules. When an arteriovenous anastosome is dilated, blood bypasses the capillary bed and flows directly into the venous circulation. The pattern of blood flow through the arteriovenous anastomosis is regulated primarily by sympathetic innervation along the control of the cardiovascular center of the medulla oblongata. Angiogenesis is the formation of new blood vessels from pre-existing vessels and occurs under the direction of vascular endothelial growth factor, or VEGF. Angiogenesis occurs in the embryo as tissues and organs develop. It may also occur at other times in the body tissue in response to factors released by cells that are hypoxic or oxygen starving. Clinically, angiogenesis is probably most important in cardiac muscle, where it takes place in response to a chronically constricted or occluded vessel. Although blood normally flows from arterioles to venules at a constant rate, the flow within each capillary is quite variable. Each precapillary sphincter alternatively contracts and relaxes, perhaps a dozen times per minute. These rhythmic changes in vessel diameter are called vasomotion. As a result, the blood flow within any capillary occurs in pulses rather than as a steady and constant stream. The net effect is that blood may reach the venules by one route now and by a different route later. Vasomotion is controlled locally by changes in the concentrations of chemicals and dissolved gases in the interstitial fluids. For example, when dissolved oxygen concentrations decrease within a tissue, the capillary sphincters relax so blood flow to the area increases. This process is an example of capillary autoregulation, and we'll focus on that in a later module. When you're at rest, blood flows through about 25% of the vessels within a typical capillary bed in your body. Your cardiovascular system does not contain enough blood to maintain adequate blood flow to all the capillaries in the capillary bed in your body at the same time. As a result, many tissues become active. The blood flow through the capillary beds must be coordinated. And we'll describe the mechanisms by which the cardiovascular center performs this coordination later in this module. Veins collect blood from all tissues and organs and return it to the heart. The walls of veins can be thinner than those of corresponding arteries because the blood pressure in the veins is lower than that in arteries. We'll classify veins based on the basis of their size. Even though their walls are thinner, in general, veins are larger in diameter than their corresponding arteries. Venules are the smallest venous vessels. They collect blood from capillary beds, and they vary widely in size and structure. An average venule has an internal diameter of roughly 20 microns. Venules smaller than 50 microns lack a tunica media, and the smallest venules resemble expanded capillaries. Medium-sized veins are comparable in size to muscular arteries. They range from 2 to 9 millimeters in internal diameter. Their tunica media is thin and contains relatively few smooth muscle cells. The thickest layer of a medium-sized vein is the tunica externa, which contains longitudinal branches of elastic and collagen fibers. Large veins include the superior and inferior vena cava and their branches within the abdominal, pelvic, and thoracic cavities. All large veins have three layers. The slender tunica media is surrounded by a thick tunica externa composed of a mixture of elastic and collagen fibers. The arterial system is a high-pressure system. Almost all the force developed by the heart is required to push blood along the network of arteries and through the miles of capillaries. Blood pressure in a peripheral venule is only about 10% of that in the ascending aorta, and the pressures continue to fall along the venous system. The blood pressure in venules and in medium-sized veins is so low that it cannot overcome the force of gravity. In the limbs, veins of this size contain valves, or folds of the tunica intima, that project from the vessel wall and the point in the direction of the blood flow. These valves, like those in the heart, permit blood flow in only one direction. Venous valves prevent blood from moving back towards the capillaries. As long as the valves function normally, any movement that distorts or compresses a vein pushes blood towards the heart. This effect improves venous return, which is the rate of blood flow to the heart. The mechanism is particularly important when you're standing because blood returning from your feet must overcome gravity to ascend to the heart. Valves compartmentalize the blood within the veins, dividing the weight of the blood among the compartments. Any contraction of the surrounding skeletal muscles squeezes the blood towards the heart. Although you're probably not aware of it, when you stand, rapid cycles of contraction and relaxation occur within your leg muscles, helping to push the blood towards the trunk. When you lie down, venous valves play a smaller part in venous return because your heart and major vessels are at the same level. If the walls of the veins near the valves weaken or become stretched and distorted, the valves may not work properly. Blood then pools in the veins, and the vessels become grossly distended. The effects range from mild discomfort and cosmetic problem, as in superficial varicose veins in the thighs and legs, to painful distortion of the adjacent tissues, as in hemorrhoids. Our total blood volume is unevenly distributed among arteries, veins, and capillaries. The heart, arteries, and capillaries in the pulmonary and systemic circuits normally contain about 30 to 35% of the blood volume, roughly about 1.5 liters of whole blood. The venous system contains the rest, about 60 to 75%, or about 3.5 liters. About 1/3 of the blood in the venous system, or about a liter, is circulating within the liver, bone marrow, and skin, and these organs have extensive venous networks that at any moment contains large volumes of blood. Veins are much more distendable or expandable than arteries because their walls are thinner, with less smooth muscles. For a given rise in blood pressure, a typical vein stretches about 8 times as much as a corresponding artery. The capacitance of a blood vessel is the relationship between the volume of blood it contains and the blood pressure. If a vessel behaves like a balloon, expanding easily at low pressures, it has a high capacitance. If it behaves more like a truck tire, expanding only at high pressures, it has a low capacitance. Veins, which expand easily, are called capacitance vessels. Because veins have high capacitance, they can accommodate large changes in blood volume. If the blood volume rises or falls, the elastic walls stretch or recoil, changing the volume of blood in the venous system. If serious hemorrhaging or blood loss occurs, the vasomotor center of the medulla oblongata stimulates the sympathetic nerves that innervate smooth muscle cells in the walls of medium-sized veins. This activity has two major effects. One, the systemic veins constrict. This process, called venoconstriction, decreases the amount of blood within the venous system, increasing the volume within the arterial system and capillaries. Venoconstriction can keep the blood volume within the arteries and capillaries at near normal levels despite a significant loss of blood. And two, the constrictions of veins in the liver, skin, and lungs redistributes a significant proportion of the total blood volume. As a result, blood flow to the delicate organs, such as the brain and to active skeleton muscles, can be increased or maintained after blood loss. The amount of blood that can be shifted from veins in the liver, skin, and lungs to the general circulation is called the venous reserve. It is normally about 20% of total blood volume.